This is week 3 of our introduction to multivariable calculus. This lesson is going to be one of the first times that we actually start doing calculus with our functions of multiple variables. So in this session, in this set of notes, we'll be doing things like differentiating and actually talking about what that means in terms of like the slope of a function when we extend it to more than one variable. So before we get into that, we should talk about what functions of two or more variables actually look like. And we've talked about this just a little bit, but in general, the notation is exactly the same. So instead of saying f of just x or f of t or whatever our variable is, now we'll say this is a function of x and y. So f of x and y is a function of two variables. We've seen a lot of these functions of multiple variables before, although maybe we didn't explicitly talk about them as being functions of multiple variables. But it doesn't matter how many variables go here. We could say f of x, y, z, or we could put a whole bunch of variables. Sometimes at a certain point we start saying something like f of, and then we just start numbering them, x sub 1, x sub 2, x sub 3, all the way up to, I don't know, however many you want, x sub 14, doesn't matter. But at a certain point when you run out of letters, you can just start using the subscript numbers. Also, in the same way that we used to talk about f of x and y being the same thing, we would say that y is the same as f of x. We can do the same thing with multiple variables, and in this case we usually use z if we've already used x and y as our variables in the function. So instead of saying f of x and y equals, I don't know, x squared plus 2y, some function of both of those variables, we could just the same say z equals x squared plus 2y. So these two are the same. And then of course if you're using more than two variables and you've already used a z, maybe you would use something else like w. Functions of multiple variables are pretty much the same as what you already know about functions. So every input produces exactly one output, and so on. All the same rules apply, so we won't really cover those things too extensively. First of all, let's look at a pretty simple example. This function of x and y is 3x squared times the square root of y minus 1. So we'll start by finding f of 1, 4. Now, if we were looking at this point 1, 4 on a two-dimensional graph, it is exactly that. It's a point on a two-dimensional graph, and it's going to give us a third number, which is where we start extending to like the height of a function. Now we're sort of growing out of the page. So you can check this as well, but everywhere that we see an x, we're going to put a 1. So I'm going to have 3 times 1 squared times the square root, and now everywhere I see a y, I'm going to put a 4. Minus 1, nothing changes for that one. And so when we simplify all of this, we find that f of 1, 4 equals 5. So our height sort of coming out of the paper at that point would be 5 steps in the z direction. And then next we'll find f of 0, 9. So same process. Everywhere I see an x, I'm going to put a 0. So 3 times 0 squared times the square root of everywhere I see a y, I'm going to put a 9. Minus 1, which turns out to be negative 1 when we simplify. And then, a little bit more interesting, everywhere I see an x, I'm going to put a t squared, and everywhere I see a y, I'm going to put a t. So this gives me 3 times the quantity t squared times the square root of t, replacing that y, minus 1, which I'm not going to simplify this very much. The t squared to the second power is just going to be 3t to the fourth. I'm going to keep the square root the way it is. Although if you wanted to use exponents, fractional exponents here, you could. But I'm just going to keep it as 3t to the fourth times the square root of t minus 1. And then last one, f of ab, 9b. So same deal. This should probably seem pretty familiar because this is the same thing that we do with regular functions when we replace an input value of x with some other number. Let's see, 3x squared times the square root of y, and then all of that minus 1. And again, I'm not going to simplify very much. The only things that I'm going to do here, I'm going to say AB quantity squared is going to be a squared b squared, and also I'm going to pull this 9 out of the square root and make it a 3. So that's going to give me 3 square root of b right here, but then I'm going to multiply this 3 with this 3, so I'm actually going to get 9 a squared b squared, square root of b, all of that minus 1. So same thing we do with regular old functions. Now the last part of this question says to find what we call the natural domain of f, which just means like no crazy restrictions on this function that you wouldn't expect, just based on sort of like the structure of this expression, what would be the domain of the function. So nothing weird is going on behind the scenes, just what is the domain of this function. Now, nothing goes wrong with the 3, nothing goes wrong with the x squared, all of both of these treated as individual functions, or even just treated as one function, 3x squared, has an infinite domain, negative infinity to positive infinity for x. Now, the square root of y does have a restriction. We know that since we're looking at y as a radicand under the square root, that y has to be greater than or equal to 0. And then the minus 1 doesn't really do anything here, so the natural domain of this function is really everything that satisfies this. So this is the only part of this that would have a problem. Now, if we were looking at this in 2 dimensions, regular old 2-dimensional graph where this is my y-axis, this is my x-axis, I'm just saying y has to be greater than or equal to 0, which means that we could lie on this line, the x-axis, that would be fine, and anything up above the x-axis would also be fine. Now, of course, in this case, we're actually like rising out of the paper and getting this z quantity going on, but we'll only be looking at sort of this half space, everything above the line y equals 0. So that's the natural domain of this function. Now, let's look at a slightly more interesting one. So find the natural domain of this 2-variable function. So f of x, y, f of x and y, is the natural log of x squared minus y. I should actually say natural log of, and when I say when I'm reading this parentheses, I would say the quantity. So ln of the quantity x squared minus y. That's how we know there are parentheses there. Now, ln is kind of a more restricted function. So remember the domain of ln, if we're just looking at something simple like ln of x, we know that x has to be strictly greater than 0. Just to remind you of that, remember that the graph of ln looks something like this. So it has this vertical asymptote here at x equals 0, never actually reaches this point. X has to be strictly greater than 0. The domain is everything over here. So we can actually just extend that to our 2-variable case, and in this case, since the argument of the ln function is x squared minus y, we can say, well, that must be strictly greater than 0. So this is a pretty simple inequality to solve, and I can actually, let's see, I'm going to move the y over to the other side and say x squared is greater than y, but actually I like to write the y first usually, so I'll say y is less than the quantity x squared. Y is less than x squared. So, so then in this case, we know exactly what this looks like. This is a parabola. It's sort of our parent function parabola that crosses through, let's see, over 2 up 4, and over 3 up 9, crosses through these points. And I'm going to graph it with a dotted line because this is a strict inequality. So if I'm graphing this domain, I'm graphing this parabola with a dotted line. Not very well. And then y has to be below this parabola. So our legal area where we can actually evaluate this original function is anywhere on these points that y is less than, strictly less than x squared. So we cannot be on this boundary parabola, we have to be below it. But all of this area is fine, and then when we extend this into 3 dimensions and actually have our z-axis sort of coming out of the paper toward you, these are all the places where we would be able to then find a corresponding height. So I don't know what the function does, but maybe like at this point we would be 5 steps above the paper or something like that. These are all of the places where we could actually find a height in the z direction of this function. Now, that sort of leads us to another interesting idea, which is how do we actually graph these things? We've done this like a little bit with vectors, but when you're actually graphing surfaces or these three-dimensional graphs and 2 variable functions, sometimes things can get a little bit complicated. So one convenient way to do this is using something called level curves. Now, you've probably seen these things called contour maps, which is where you have like, let's see, this is going to be terrible, but it's where you have something like maybe a hill or something on a map, and then you have these like level curves. You have these curves inside that tell you like, well, it's getting taller and taller and taller here, and like this is the tallest part of the mountain and this is the shortest part of the mountain. That's exactly what we're going to do on a 3-dimensional graph here, which is weird because we're actually going to start by graphing it in just 2 dimensions. This is a 2-dimensional graph, so we'll start here and then we're going to graph these things called level curves, and these little level curves, just like on a contour map, tell us the different heights of our function at certain places. So we have this function of 2 variables, f of x, y, equals 4x squared plus y squared. We're going to do this using level curves of heights 0, 1, 2, 3, 4, and 5. And what this means is when I say heights, what I mean by heights is my z value. So I want my z value to be 0, 1, 2, 3, 4, and 5. So I'm just going to say, well, since f of x, y, remember this is the same as z, so everywhere I see my f of x, y, or z, I'm just going to put a 0 to start with. So I'm going to start with this height of 0. So 0 equals 4x squared plus y squared. So we have to think about what this is. What does this graph look like? So 0 equals 4x squared plus y squared. What would give us those values? Well, you have a whole bunch of options. You could either think about, like, is this a function that you know? Which it kind of looks like a circle. I mean, we do have an x squared and a y squared. It tells us this is going to be pretty curvy. But then we have the 4 in the front, so it's not a circle. That might make you think that maybe it's an ellipse or something, but usually when we do conic sections, we want this to be equal to 1. So remember, you can always fall back on something like, a t-chart, something that would make all of this equal to 0. And one pretty obvious point is 0, 0, and actually that's going to be the only thing that solves this, because when I square these things, they both would turn positive, and the only way that I can make this equal 0 is if both of my original values were 0. So I'm going to start by just putting a point there at 0, 0, and that is going to be I guess we'll call it the level curve, even though it's not really a curve, it's just a point that corresponds to my height of 0. So then I'm going to do this again, except I'm going to use a height of 1. So now instead of setting the function equal to 0, I'm going to set it equal to 1. So 1 equals 4x squared plus y squared. This looks a little bit more maybe like an ellipse to me, because it's equal to 1, which is how we always want a conic section. And then I have my 2 squared values. So let's see. To change this into maybe a form that I can graph, well, I can do a couple things. I can make an x, y, like a little t-chart. Or I could solve this in some other way, but for right now, I'm actually just going to make a t-chart. So let's see. If I plug in an x value of 0, y has to be 1. If I plug in an x value of 1, that's not terribly convenient for y. So let's change that to something else. Let's see, let me put this point on here. X is 0, y is 1. Also, I guess the same thing works. I'm going to do x equals 0 before I move on, and then y equals -1, just because the negatives of this are going to do the exact same thing. So I can square, because when I square the negative, it turns positive. Now, if I want to put in an x value of 1, that's going to make y really small, because I'm going to have 1 equals 4 times, and then 1 squared. Actually, sorry, that doesn't even work. We can't have an x value of 1. So let's not do that. What else can I put in for x? These are going to have to be very small values. Well, what if I put in 1/2 for x? If I put in 1/2 for x, that changes this to 1 equals 4 times 1/4, which is going to give us 1. And then I would have to add in a y value of 0, and I could do that also with -1/2, and then a y value of 0 as well. So that's going to give me something that looks like this, and it turns out it is an ellipse, like we expected. It's just a skinnier ellipse. So there's my next curve. That curve represents a height of 1. Now if we were actually graphing this, I'd want to be stepping 1 step up in the z direction, so like sort of out of the paper. Then I can do the same thing with 2, so I'm going to go 2 equals, and then 4x squared plus y squared. And now I'm actually going to use what I know about conic sections. Now when I'm dealing with conic sections, I want to have everything equal to 1. So I'm going to divide every single piece by 2, and I'm going to make this 1 equals 2x squared plus y squared over 2. And actually when I'm dealing with conics, I like to have fractions, so I'm going to write this in a really weird way. 2x squared over 1/2 plus y squared over 2. Now I only wrote this on the bottom here just because I like to have ellipses in this fractional form. So I don't know if you remember this, but ellipses always have the form 1 equals, and then we have x squared over a squared plus y squared over b squared. And when you're graphing this, your a value, this is a squared on the bottom, but your a value is sort of your horizontal vertices. This is a negative a and this is a positive a. And then the b value on the y-axis gives you sort of your y-axis vertices of the ellipse. So I've got that exactly in this form. In this case, our 1/2 represents our a squared, and 2 represents our b squared, which is a little bit weird, just because that gives us strange values for a and b. So like in this case, a is going to be 1 over the square root of 2, and b equals just the square root of 2, which is not going to be very pretty, but we can still do it. So remember, square root of 2, even though it's irrational, is about, what, 1.4 or something, so, or 1.41. So 1 over 1.41, I'm just coming up with like an approximation. So this is about 0.7, so that I can graph it. And then the square root of 2, like I said, is about 1.41. So I'm just going to graph these things and make an ellipse. So 0.7 is kind of really close out here. It's a little hard to graph, and then 1.41 is like somewhere like right there. And this gives us another very skinny little ellipse. Now the height of that level curve would be 2 steps off of the paper. If I was actually graphing this in 3 dimensions, I would go up 2 for this red curve. And then I'm going to continue this. And one thing that you could do, if you want, is pause the video and do this on your own for 3, 4, and 5 and check your work at that point to see if you're kind of on the right track here. But I'm going to continue doing this. So let's see. These are all going to be ellipses. And they're all going to have, I think, irrational values except for maybe the 4. But I'm going to keep doing this anyway. So 3 equals 4x squared plus y squared, which is going to give us 1 equals 4x squared over 3 plus y squared over 3. And in other words, 1 equals x squared over 3/4 plus y squared over 3. So in this case, A is the square root of 3, well, the square root of 3/4, I guess, so the square root of 3 over 2, and then B is the square root of 3. So that tells us that B is about, what, 1.57 or something? Square root of 3, or sorry, 1.73. So I'm going to go up 1.73, not quite to 2, and there. And then the square root of 3 over 2 is about 0.86, so we're still not out at 1, something like this. So it's getting taller faster than it's getting wider. And then I'll do a height of 4 in green, which is going to give us 4 equals 4, this is the only one that might turn out sort of nicely, plus y squared. When I divide everything by 4, I get 1 equals x squared plus y squared over 4, which kind of tells us our a value is 1, so I'm actually going to make it right out to 1 on either side there, and our b value, since b squared is 4, is going to be up here at exactly 2, like so. So there's our height of 4. And then our last one is going to be a height of 5. And in this case, we're going to get 1 equals 4x squared over 5 plus y squared over 5. So our a value is going to be the square root of 5 divided by 2, and our b value is just going to be the square root of 5. So the square root of 5, actually don't know the approximation for that one. Square root of 5 is what, 2.23, so I'm going to go up here 2 point something, 2.23, about 2.23, and then the square root of 5 over 2 is just past 1 on either side on the x-axis. So there is our level curve. This last one is a height of 5. So if I were graphing this in 3 dimensions, everywhere on this black ellipse, I'm going to be walked 5 steps up in the z direction. And that's how we graph with level curves. Now at this point, you are ready to do, let's see, a whole bunch of the problems. So problem 1, actually, you might want to change this to just a regular 2-dimensional graph for level curves. It might actually be easier if you just draw an XY plane like that for number 1, because I guess setting you up with a 3-dimensional graph really doesn't, you can do it like that, but it's just your preference. So number 2 is also graphing using level curves. You'll notice that numbers 1 and 2, like the actual function, is very similar, so just think about maybe what this plus 1 inside the square root would do. Number 3 is the same thing, so at this point you're ready to do problems 1, 2, and 3. So you can do those now, or you can continue on with the video part 2 and then come back to all the exercises in the end.